Hello, my name is Kevin Drain.
My name is Brandon Houston.
And I'm Nicholas McKnight.
And today we'll be talking about unimolecular diffusion. The definition of that is an instant molecular diffusion in a binary mixture and occurs when equal numbers of molecules of the two substances are moving in the opposite direction.
Okay, so our first step in starting off with understanding unimolecular diffusion, we're going to start off with the velocity. So in the velocity, for our first equation, this is the Jz is our molar flux. We're going to assume that this is our velocity of solution A, and Ca is the concentration of A. So as you see, we go down and break it down even more, VA, again, like I said, is the velocity of solution A, and VAM, I was informed by my partner that VM is, what exactly?
VM is the molar average velocity of a mixture.
So that's what VAM is as well. So going down, breaking down our equations for velocity in different ways, we could manipulate an equation to get velocity. We got our concentration of A times our velocity of A is equal to CAVAD, which is also equal to the molar flux, plus the concentration of A and
molar average velocity.
the molar average velocity. I'm gonna remember that. And so again, down here you can see we just implemented that in there. And then the molar average velocity is equal to the summation of, I'm not sure what NI is.
That's the flux of I.
Oh, so the NI is the flux of I. Yeah, that makes sense. Over the total concentration. And so, again,
and then just rewriting.
Yeah, that's basically just rewriting, saying that the
molar flux of A,
molar flux of A plus molar flux of B over the total concentration will give you the
molar average velocity.
Molar average velocity. So, bringing what we know over here will give us our total mass transfer equation. Because so basically, unimolecular diffusion is just another mass transfer equation. So our final equation will be the flux of A. No. NA is the flux of A. NA is the flux, right?
Flux of A.
Yeah.
So it will be the flux of A equals to the negative concentration of the diffusion coefficient times the gradient plus the concentration of A times the summation of the flux of A and B over the total concentration. And that will give you your total.
And what we have right here is an example of a tank, which is this is literally just the top layer of the liquid. And what we have going on here is A, which is our liquid, and B, which is our air. And it's diffusing off, giving off oxygen, kind of somewhat mixing, but not affecting the elements in the oxygen.
I think you want to say that. I don't think we want to just say oxygen because there's a lot of stuff in air though.
Okay.
We can just say air. I think air would be better.
Okay, well, air. And here we have, like I said, it is diffusing offensive oxygen and air.
Yeah. So.
And for our assumptions, we have a steady state. B is negligible, solubility Na, MeZ is 0. A
So
and B
hold on. We say that B is negligible in the solubility of A because this solution literally is going out, right? So like let's say if it's evaporating or whatever it is, it's literally gonna be mixing with the air. So basically, if B is air, just like if any other equation when it's equal to air or atmosphere, is going to be 0. That's why B is negligible in A. And so, of course, A and B don't react because B is just the atmosphere. It doesn't react with a solution. And then we have...
And then no accumulation. That's just basically saying that our liquid A is diffusing into the air, and it's an open tank or container. So everything that's diffusing is leaving the container and leaving with the current of the outside air of the container. So there's no buildup inside the tank.
Yeah. So if you taking what we know, what Nick just said about that, if you put it to your general mole balance equation, you'll get that N equals out.
And that is it for UMD. 1. Hello, we're back to talk about the equimolar counter diffusion.
I like that better. Okay, so we're going to start off with the main points, the main 4 points that what we know about equimolar counter diffusion. The main thing that you know in an equimolar counter diffusion is that your concentration, your temperature, and your pressure are constant. Simple as that. With knowing that, you know that your system is closed. Okay? So, with a closed system, and with all that being said, oh man, sorry, excuse me. We also know that the concentration of A, the initial concentration of A is greater than your initial concentration of 2. Also being said, your initial pressure of A is greater than your initial pressure of 2. But, as you can see here, it's the almost basically the complete opposite when it comes to B. That's not supposed to be like that. Who wrote that like that? Oh, that's cool. So, with that slight little modification, we see that the initial concentration of B is greater than the final concentration of B. It's the same as with the pressure, the initial pressure of B is greater than the final. So, with that being said, this can all be explained because of the molar fractions and the mass flux of A is to the right. So, with that basically like explains this with the molar fractions. So basically, like I just said, the mass flux of A is to the right, so therefore it's positive. Which means, since this was basically the exact opposite, that the mass flux of B will be negative.
Okay, and so looking at our picture here, the molecules of A are diffusing to the right, and the molecules of B are diffusing to the left. Because the pressure remains constant, the net moles of A diffusing to the right and the net moles of B diffusing to the left would equal each other. If this were not true, then the pressure would not remain constant. And because it is true, that's why our JAZ is equal to our negative JBZ. And then also the general equation for equimolar diffusion, we have the flux of A going in the B direction is equal to the concentration times the diffusion coefficient times the gradient.
And also for our assumptions, we have that there will be a net flux of A to the right, as Nick said, and for the equation, B does not equal 0 in this scenario, and the magnitude of the net flux of A is equal to B, and the net flux of A is opposite in the direction to net flux of B.
So I also want to reiterate that with this being stated, this could be the exact opposite and the equation will still work.
Thank you. So
Okay.
Today we'll be talking about molar flux for this next video. So starting out, we'll start with the momentum flux, but these are just 2 equations that are derived from that, which will be later on explained by my friend Brandon. So here we have the momentum flux, which is equal to the negative viscosity versus times dV over dy, which is the velocity gradient. And for the heat flux, it equals the negative K, which is the thermal conduct. And for dt over dx is the temperature gradient. Now this chart here you see is different spots of liquids. It starts out as like this, then it gradually goes down as you see, but sooner or later it'll be fully covered like that as you see at the top. And there's something called, what is it called? When this it starts to disperse throughout the whole
So that's
room, like we were talking about.
So basically, it's diffusing time equals 0. So by the time so much time elapsed, it would have been done diffusing, and the entire room would be at a
Filled
certain
with whatever that liquid is.
yeah.
That's a good one. Okay. So, no, it's not easy.
Okay, so we have mass transfer from a high to low concentration. Net mass transfer equals 0
When the concentration is uniform.
when the concentration is uniform, and the transfer rate is proportional to the area.
And that is all connected to this chart. So, excuse me. Earlier, when Kevin was talking about these two equations, these two equations are just other mass transfer equations that kind of just break down specific things. So, like you see momentum and heat. But what we're mainly focusing on today is the general molar flux equation. And so, with the molar flux equation, it is represented as JAZ, which is what is that again?
The molar flux of
So
A.
yeah, the molar. I'm sorry, the name's right there. So it's the molar flux of A with the in the direction of Z equals to the negative diffusion of A in B multiplied times the concentration area. Now this is negative because of the high because it starts as a high concentration and goes to a low concentration. So, and right here we just have different kind of derivations of the this general equation. Even though the general equation is our main focus, this is just like breaking down. Like, so if you wanted to find your mole fraction, that XA would go in right there, and if you wanted your mass fraction, the two main differences is you're gonna have rho in here for density, and you're gonna have your WA in which I think it's mass, if I'm not mistaken. It's definitely mass. So that's basically all we have for you guys today. This is a general equation. Everything starts with this and goes into everything else that we talked about today.
Thank you again. My name is Kevin Drain,
Brandon Houston.
And Nicholas McKnight.
and this is Separations.